Okay, we'll get started. So in last class, if you remember, we have been looking at the capacitive DACs, right? And we saw that the architecture is going to look something like this, right? So you have an array of caps, and this array can either be entirely binary weighted, but we know what is the disadvantage. You will end up with non-monotonic behavior. So in practice, usually you have a segmented array. Okay, so the top MSBs will be uh, binary thermometric, and the others will be binary weighted. Okay, so we saw what is the how does this work. Basically, you have a capacitive divider, and let me just show you I didn't do the derivation of how it happens, but let me just show you. And so one of the things that we saw was the maximum capacitance. So even if you start off with, let's say, a very small value of 100 femtofarad, right, as your unit capacitor, if you're using a 12-bit DAC, the max capacitance become the biggest capacitor, biggest single capacitor that you'll be using is 204.8 picofarad, and the total amount of capacitance on chip will be 400 picofarad. Okay, this is a very large amount of value, which is pretty much not feasible in this in typical IC. Otherwise, you will have a very large IC. Basically, it's a waste of area and waste of money, essentially, right? So we will look at what is called as a split cap DAC, all right, and we will also look at the other things, other, yeah, yeah. There are a couple of other DAC architectures. Hopefully, I'll be trying to wind up our discussion on D2A converters with today's lecture. Okay, and so let's get started with that. Now, if you look at a capacitive array DAC or a charge sharing DAC or a charge redistribution DAC, we saw that essentially you have capacitors either connected to VREF or they are connected to ground. Okay, so there is a switch, right? This switch will, okay, let me draw it a little better. Okay, this is ground, this is VREF, and there is this switch. So the switch can either connect here or connect this side, right? So if it is DN, it will connect to VREF. If it is DN bar, or let's just say DK bar, it will connect to ground. If it is DK, it will connect to VREF. Okay. So essentially, so like this, you have a bunch of arrays. Okay, let's just talk about binary weighted arrays. We know how to do segmentation, right? Now essentially what this translates to is that you have VREF, you have some C1, and you have another C2 to ground, and this is your output node. So we know that this is connected basically to a unity gain buffer, right? So what is this V out? So I want to show you how this V out comes so that you get an understanding of how capacitors, charges work and all that, right? So what is the total charge which is stored in the combination of C1 and C2? It is basically C1 C2 divided by C1 plus C2, the effective series capacitance, into VREF, right? This is the total charge that has been stored in this entire capacitive array. Now what happens, we are interested in finding out what is this V1 and what is this V2. Okay, now this charge of Q, let me say Q total, right? It has flown, I mean, what is charge? I mean, charge is basically what? The integration of current over a period of time, right? So that current which has charged up these capacitors has flown through both C1 and C2, okay, for the same amount of time, and that is how this effective capacitance of C1 parallel, I mean C1 C2 divided by C1 plus C2, the series combination of C1 and C2, has been able to store this amount of charge of Q total, right? So which means the same amount of current has flown through both C1 and C2. In other words, the same amount of charge is there on C1 as well as C2, right? So current flow has caused, let's say, a certain amount of positive charges that will induce a certain negative charges here. So that will attract some positive charges, and then that will induce another negative charges here. So that is how capacitors work. So V1 can be written as what? Q total into or divided by C1. Same way, V2 can be written as what? Q total divided by C2. So what will this work out to be? It will be C1 C2 divided by C1 plus C2 into Vref, and V2 will be C1 divided by C1 plus C2 into Vref. For us, V2 is basically our V out. Okay, so it is basically the top capacitor divided by the sum of the whole capacitors. Okay. Now, this is the way that this charge sharing DAC basically works. Now, the interesting point is the problem that we faced is the MSB caps are too large. Right? I showed this in previous class also. It is reaching some 200 and something picofarad. Okay. Now, it is difficult to reliably, design. I mean, if you have a very small capacitor, right? The what is the problem? Let's say you try to have a 1 femtofarad capacitance. What will be the problem? Let's say unit capacitance is 1 femtofarad, right? Then the C n minus 1 bit, which is basically the, let's say C0 is this one. What will this be? 2 to the power of n minus 1 into 1 femtofarad, right? So this will be around, let's say for a 12 bit DAC, this will be what? 2 to the power of 11 into 1 femtofarad, which is 2048 femtofarads, which is what? 2.048 picofarad, which is okay. This is manageable, right? But what will be, do you think there will be a problem? Can we use a unit capacitance of 1 femtofarad? Anybody? Is it okay? So all of you are saying that it is okay to use 1 femto? Or are you guys saying no, you should not use 1 femto?
For higher bits, it will be difficult, right?
That's what, higher bits you are getting 2 point. See, earlier example I gave 100 femtofarad is the unit capacitance. Now I have reduced it by a factor of 100. Okay, I am saying now the unit capacitance is only 1 femtofarad, a very very small value. So I'm asking, and also the MSB capacitor is very much within the range, right? It's around 2 picofarad, which can be easily synthesized, easily implemented. So do you think it is okay, or do you see any other problem?
High noise.
Why will you have high noise?
Because lesser capacitance.
Sorry?
Because of the lesser capacitance with high fluctuation with the frequency.
First of all, a capacitor does not have noise, right? Thermal noise is there only in resistors, correct? So noise is not present in capacitors, right? Of course, it will have some parasitic resistance, but that's quite negligible. I mean, it's a small value. What you
Still,
talked about,
output
yeah, just a minute. Let me.
voltage will
Yeah, output voltage will be.
increase.
Why will it increase? It's anyway ratio, no? The output voltage is C1 divided by C1 plus C2. So, as long as you preserve the ratio, what is there? And as for the other point that somebody brought up, what did you say? It is the capacitor, the high frequency, it will change easily. So the impedance of a capacitor is what? Xc is 1 by j omega c, right? So as c reduces, your Xc will only increase. So what do you mean by high frequency noise? Okay, so I want you to think in terms of layout. Okay, so always as VLSI engineers, even if you are a design engineer, you should always keep layout in mind. Okay, if you design without layout in mind, it is like what shall I say? Uh, it's like riding your bike without looking at the fuel tank. Okay, I mean fuel level. You don't know when you will, when your bike will totally stop. All right. So it's a crude example, but that's kind of how it is. If you don't know how the layout works, okay, you cannot do proper design. All right. So let's say I'm having a 1 femtofarad capacitance. So typically, if you say MIM density, it will be 1 femtofarad or 1 to 2 femtofarad per square micron. That is to say, if I put a 1 micron cross 1 micron MIM, I will have 1 femtofarad. Okay, let's just take 1 femtofarad for now. Okay. Now, you have to connect this capacitance, right? So you'll have 1 femtofarad, then you'll have 2 femtofarad, and in last class I mentioned that you should not put one, you know, you should not put one 2 cross 1, right? This will be 2 femtofarad, but then your matching will be bad. Here matching will be bad. So what should be done? I mentioned this in last class. How should you implement 2 femtofarad?
By unit capacitances.
Correct. So you will put 2 unit capacitance, right, and you will connect them together. Okay, right. So let's say however you connect it. Okay. Now, like this, you have lot of of course, this is possible. You see, when it comes to 2 picofarad, you cannot have all 1 femtofarad. We'll come to that. Okay. Let's say I have one more thing. Okay, so this is 2 femtofarad, this is 4 femtofarad. All right, so this is, let's say, D0 for D1 and D2. Let's stop with this now. Okay, now you have to connect all of them, correct? So how do you need to connect? You will have one piece of wire. A wire is basically what? It's a rectangle, cuboid, whatever. Okay, and in layout it will be it'll be like a path, right? And then you have to come to a switch, right? So you will have a switch, which will basically be a transistor, right? Let's say this is the drain, this is the source of the transistor. So this is connecting to, let's say, the ground line, and you'll have one more transistor. Let's say this is the drain, this is the source, connecting to, let's say, the VREF line. Okay, so now you have to connect like this, right? Now the same thing has to be repeated for all the capacitors. Okay, so here what you will do, you will basically, let's say, the top plate, and here again what will happen, you will have the top plate which is connecting, right? So let me just remove this. Let me just move things around so that I can demonstrate better. Okay, so this is the 2 femtofarad capacitance, right? So let's say you have to put like this, and then you have the switch arrangement. Now you will have what, right? And now you have the same switch arrangement. Here what happens, let's say this is the top plate of the capacitor, right? This is how you would probably connect, and then you will connect it to what? This is going to the op amp. So basically you'll put one contact, this goes to the gate of the op amp's transistor, right? Now if this is 1 femtofarad, all this routing, the reason I drew all this routing is, right, all of them will have some small resistance anyway. Now we are not bothered about we are not looking at the resistance now. See, there will be a distributed capacitance. Okay, it's not a lumped capacitance, it will be distributed, right? Because spatially this line is running for a longer distance, and for all this, what did I do? I just drew for 3 bits. Okay, think of it in the scale of a 12-bit DAC. All right, so how many elements you will have and how they will all be connected together, right? Now the parasitic capacitance itself will be, the parasitic capacitance on this, let's say, signal line, okay, this V out line itself will be quite significant. Okay, so a 1 femtofarad change in that, a 1 femtofarad capacitance either getting connected to Vref or ground will hardly make any difference in your output voltage. Okay, so let's say for example this routing capacitance is, let's say, totally it's coming to around 5 femtofarads. All right, effectively this capacitance on the V out line connecting some, let's say, an 8-bit DAC or something is easily coming to some 5 femtofarad, for example, okay, or 10 femtofarad. Okay, so how does it matter whether 1 femtofarad gets connected to Vref or ground? It basically, it's like, it gets submerged in the parasitics. So what will happen is your DNL and INL will be very bad. Okay, so for your LSB transitions, you would have expected what? So because this is all about charge sharing, right? So if you, in the absence of all the parasitic capacitance, you have C1 divided by V out is given by C1 divided by C1 plus C2 into Vref. Okay, now what are you having? C1 plus C2 plus C parasitic into Vref. Okay, and so when it is changing, your DNL is going to get really bad. Okay, on top of it, throw in variation and things like that. Okay, so which is why it is not feasible to put extremely low. In fact, if you didn't have all this parasitic capacitance in the routing, right, you can go for very arbitrarily low things. You can start with 10 attofarad capacitance also, right? So the whole thing becomes, your DNL becomes very small. Let's say you wanted Vref divided by 2 to the power of n as your resolution. Now because of the parasitic capacitance in the denominator here, right, you will get much lesser than your LSB value. Okay, so this is the problem, which is why you cannot use arbitrarily low values of capacitance. Okay, and especially for the smaller capacitors, you have to do extremely careful layout. Okay, so let's say you use bigger capacitors, will be, let's say, bigger unit cell sizes and so on. Okay, I drew the parasitic capacitance only on the top plate. Actually there will be parasitic capacitance everywhere. Okay. So the individual capacitors probably will be in the range of attofarads and so on, but then you put it all together on a very large line, you get a larger capacitance. Okay, so this is the problem. So you have to use a reasonably high value of unit capacitance. That's the moral of the story. Okay, so but if you use that, let's say if you use, let's say, 50 femtofarad or 25 femtofarad or something like that, your overall area blows up like anything. Okay, so in order to solve that problem, people came up with what is called as a split array or a split cap array, whatever you call it. Okay, now let me first give you the circuit, and let us take some use cases and convince ourselves that it is actually going to work. Okay, so that's the way we are going to do this. All right, so Okay, did I talk about reset in the? Okay, let me do that here. Okay, so here, as the name suggests, what we are going to do is we are going to split the DAC array. Okay, so let us take for example a 6-bit DAC. All right. So what we are going to do is we are going to split it into 3 LSB bits and 3 MSB bits. Okay, so this is not segmentation, they are still binary weighted. Okay, but we are kind of going to split it, and let me draw the circuit diagram. Let's say this is C, this is 2C, this is 4C. Okay, and you know that we usually put one more C, right, for the LSB side. This is the top plate. Okay, so let's say one is ground and the other is VREF. Okay, now what I'm going to do is I'm going to split it by putting a series capacitance. Okay, let's call it as the attenuation capacitance. Okay, there is a series capacitance, and then what you have is again you have C, 2C, 4C. Of course, this is going to our this thing. Okay, and this is your V out, and also what happens is you have a, of course, this is true for the other things also. This is your reset switch. Reset switch, what does it do? It just connects the, shorts out all the capacitors to ground. Okay, so this side will also have a reset switch. I think I forgot to add the reset switch in the previous thing, but of course it's understood. Okay, now what is claimed is, okay, oh sorry, yeah, this is grounded. Okay, now what is claimed in all these things is, let me just finish this grounding. Okay, what is claimed is, let's say this is D0, D1, D2. This portion is just like how you have for your normal capacitive array. Okay, and after the attenuation, when you go from the left to the right, so this becomes, let's say, D3, D4 and D5. Okay, now so we have to, and this attenuation capacitance, let me write C atten, the value is given by this. Okay, it is given by sum of LSB side LSB array caps divided by the sum of MSB array caps into the unit capacitance C. Okay, so in this case, what is the thing? What is the sum of the LSB array caps? You have 4C plus 2C plus C plus C. So you have 8, right? And what is the MSB array? 1 plus 2 plus 4, which is 7 times C. Okay, so this attenuation cap is given by 8 by 7 C. Okay, now let us see whether it really works or not. Okay, so let us, in order to convince ourselves, let us take some codes. Let's say first code is MSB. So usually, to figure out whether it is working or not, what you will do, you will turn on the MSB and keep the rest as zeros. Okay, so MSB is on and all the rest are zeros. What do you expect? What is the expected value here? What is the expected value theoretically?
2 raised to n minus 1 by 2 raised to n VRF.
Correct. So what does that evaluate to? 2 raised to n minus 1 divided by 2 raised to n into VREF. What is this? Come on guys, it's a simple thing, right? You have 2 to the power of n minus 1 in the numerator, 2 to the power of n in the denominator.
VREF by 2.
That's it. VREF by 2. Intuitively also you know that MSB is basically the midpoint, right? So if MSB is 1 and the rest 0, MSB 1 is basically for VREF by 2. That's it. So if you have MSB 1 and all the rest zeros, 1 and all zeros code, your output has to be VREF by 2. Okay. So now let us figure out whether that is the case. Okay. So if that is the case, what happens? So all the LSB bits are connected to ground. So the effective LSB bits is how much? You have the fixed capacitor C, and then you have 4 plus 2 plus 1. Totally you have 8C connected to ground, and you have 8 by 7C in series. And here what do you have? You have 4C connected to VREF, 3C connected to ground, right? 3C connected to ground and 4C connected to VREF. Okay. And what is your output voltage? This particular node V out is your output voltage. Okay. So let me redraw this. Let me just redraw this as what? Vref 4C, right? This is the output node. And then what do you have? You have 3C to ground. You have a series combination of 8 by 7C and 8C to ground. Okay. Now what is this equivalent to? 8 by 7 in series with 8. Can you quickly calculate and tell? 8 by 7 into 8 divided by 8 by 7 plus 8. How much will you get?
1.
No, you will not get 1. How will you get 1? It's a series combination, no? So you'll have 64 by 7 in the numerator. This is what? 56 plus 64? Sorry, is this 1? I'm sorry. Yeah, you have 7 8s are 56. 56 plus this one is 64. Yeah, you're right. I'm sorry. I'm sorry. Yeah. You have 1. Correct? Uh, you're right. So this is 1C. So then what happens? I'm sorry. Yeah. So you have 4C, and here you have what? 3C in parallel with 1C, which is 4C, right? So what is the value here? Vref, V out can be written as Vref divided by 2. Correct. So this proves that our circuit is working for this particular code. Let's just take another, let's say, arbitrary code. Let me give you one more code, or rather, not an arbitrary code. Let us see whether one LSB is giving us the right thing. Okay. So that is to say, all zeros and 1. Okay. Now, what is all zeros and 1? What is the expected V out? What is the expected V out, guys, if you have LSB equal to 1?
Vref by 2 raised to n.
Correct. Vref by 2 to the power of n. Here n is 6. So what will you get? Vref divided by 64. Okay. So let us see whether we are getting that. Okay. So so here again what happens? You have Vref connected to a single C, and you have, what is the capacitance connected to ground here? You have C plus 2C plus 4C, that is 7C, and you have 8 by 7C, right? And what is this thing? This will be what? 7C again. Okay, 7C again connected to ground. Okay, this is your V out. Now this is a little more messy network to solve, but let's try to solve this, right? Okay, so what is this V out here? So how you solve this is basically you find out, let's say this is some Vx. Okay, first find out the effective capacitance at Vx. So what is the effect? And let's say it is C divided C with some effective capacitance here at Vx. So let's find out Vx first. What is this effective capacitance? So it is series combination of 8 by 7 and 7, right? So 8 by 7 into 7 divided by 8 by 7 plus 7. So this is 8 divided by, you'll have what, 49 plus 8, which is 57 divided by 7. So this becomes 56 divided by 57C, correct? That plus 7C, because both are in parallel, right? So what will you get here?
One or five by seven.
Okay, 105 by 7C.
Sorry, sir, no.
Okay,
455 by 57.
455 by 57C. Okay, so this is your, so your Vx can be written as what? Vref divided by the other capacitor C divided by 455 by 57C plus 1C, right? The total capacitance. Now with this you can write what is V out. Okay, so if V out can be written as what? Vx into 8 by 7C divided by 8 by 7 plus 7. Okay, so you can, work it out, and you can convince yourself that it is indeed Vref divided by 64. So completed. So in the interest of time, I'll just quickly finish this. So this is what is called as a split array DAC, and sometimes people use multiple splits like this. Okay, maybe two attenuation capacitances and so on. Okay, and this is a very good solution for larger resolution capacitive DACs. Okay, now any doubts, any questions? All right. So now let's move to what is called as a cyclic DAC. Okay. So we'll just look at the topology, and we will see how it works. So cyclic DAC means you have only one bit DAC. Okay. So what you do is you have you start off with, let's say, a parallel to serial converter. Okay. So let's say you are getting dn minus 1, dn minus 2 all the way to d0. This is converted to a series. This is converted to a series bit stream. Now what happens is, as the name suggests, you're kind of going to go around in cycles. Okay. So what happens is, if let's say dk is 1, it connects to Vref, and if dk is 0, we connect to 0, ground. Okay, now this value is added to an existing value. Okay, so here you have one more sample and hold. All right, and you take this, you divide it by 2, and then you add. Okay, so say VA. Okay, so how this works is, let's work kind of go through its operation. Let's say initially this voltage VA, okay, or rather, okay, the V out is here. Okay, now initially it is all 0. Okay, so let's say you start with the LSB. So LSB first. So if LSB is 1, you add Vref to 0. Okay, and you sample it, and then you divide it by 2, okay, and then you again go in the next iteration. What happens? You have the D1. Okay, so D1, depending on whether it's 0 or 1, you either add vref or you add 0. Okay, again you need the sample and hold, because otherwise how will you keep track of which bit is coming in? Okay, so there is a clock which is running, and that will synchronize your serial to, I mean, parallel to serial converter also. And then so in the first cycle you do LSB, and when the second cycle, what do? You are adding half times the existing value to the next one. So like that you keep building up your voltage, and then you get the output thing. So is it clear how the cyclic DAC works? So every bit is either vref or ground, and once you sample it, you divide it by half before you add with the next bit. Okay, so even the final value will be divided by half. So if you have, let's say, 1 and all zeros, what will happen? You'll have 0 circulating around, and then you'll have finally 1, it will be vref, and then you'll divide it by 2, and then you finally get the output. Okay. So V out of n can be written as dn minus 1 vref plus half times Va of n minus 1. Okay. So the current output is going to be the previous voltage, half of it, added with the previous, I mean the existing voltage, the whole thing divided by half. Okay. So whatever was there earlier, right, Va of n minus 1, the previous value, plus the incoming bit, that divided by 2 will be the output. Okay. All right. So now here, of course, n is, so how many cycles will it take for this to fully converge? For an n bit DAC, how many cycles will it take? N cycles, right? So there is what is called as latency. Okay, or there is also, you get output once in n cycles. Okay, so if you are okay with that, you can use, of course, here what is critical is the divide by 2. This is very critical, right? If you don't do a proper divide by 2, what will happen? You'll end up with DNL errors and INL errors, right? So of course the sample and hold and all these things are there. Okay, so now if you don't want this delay, or let's say if you will get the output only for, so this is the end latency, right, and also you get output once in n cycles. Okay, so that's your throughput. I hope you know the difference between latency and throughput. Throughput is how often do you get the output, right? So here it is once in n cycles you get the output, and latency is from the time that your digital bit is given to the time that your analog value is ready. That is called latency. Okay, in all the previous things that we saw, you have only one clock cycle. Okay, you have one clock cycle, either things go to vref or things go to ground, the op amp settles, that's it, you're done. Okay, but whereas here what happens, you have n cycle latency, and also throughput is also 1 in n cycles. Now suppose you want to improve the throughput. Okay, you go to, what you do is, it's called as pipeline to DAC. It's the same concept, all right, but only thing is you kind of stretch it out. Okay, so in other words, let's say, let's unroll the cycle. Okay, just think of it, this is like one side, a cycle which is just spiraling around. If you just kind of unwrap it, what will you get? You have a sample and hold which is going to sample either vref if it is d0, or ground if it is d0 bar. Okay, and this is going, oops, okay, this is going to a gain of half, and then what will happen, you add this to d1 d1 bar, right? And then again you sample it, divide by 2, and then you do it, okay, till you have dn minus 1 going to vref, dn minus 1 bar going to ground, right? And you have sample and hold, and you have gain of half. This is your vout. Okay. Now what is the difference? Basically it's the same thing as the previous one. All right, the previous one, here also you have a latency of what? N cycles. That is, if you give a digital input, so you should basically have some logic which delays the MSB outputs, right? MSB bits. So basically the, it kind of propagates from here to here to here, and then from here to here, like that. Okay, so you have latency of n cycles, but then your throughput is one output per cycle. Okay, so for every clock cycle you will keep getting one output. Okay, but the latency, that is from the time you give the digital code to the time you get the analog output, it takes n cycles. Okay, so this is what is called as a pipelined DAC. And so with this we will complete our discussion on DACs. Okay, next Friday, not tomorrow, next Friday we will have the presentations for our sample and hold switch. Okay, so you'll be evaluated for 10% of your total credit. All right, and your next assignment, I will put it on the Moodle page. Your next assignment will basically be more like a term paper kind of thing. I will discuss those things later. Okay, so you will take some journal papers on DAX that I will provide. So two of you will have to go through one paper, and maybe one team can have 3 people, the others will have two people each, and you have to go through that paper, understand how that paper works, and then you have to give a presentation explaining how it works. Okay, so any doubts, any questions? All right, okay, thanks everyone, and we'll meet in the next class in a few minutes.
Thank you, sir.